So I would like to use this video to summarize the general mechanisms of action for the hydrocarbons. So we have here an alkane to start with. We started here, right? So again, just to clarify, we have discussed that alkanes are generally non-reactive because all of the bonds are sigma. You do not have pi bonds here, which can be used as an avenue for either an electrophile or a nucleophile to attack. There's no reactive site. The only way that you could have an alkane react is if you have a presence of halogen, such as chlorine, in the presence of sunlight, because in that case you will produce free radicals. And if you produce free radicals, you would then have chlorine free radicals here attaching to this. And we know that alkanes will now undergo free radical substitution because the chlorines here will substitute the hydrogens one by one. So it's as if each one of these hydrogens are being depleted by the chlorine, are being substituted by chlorine in order to come up to a final product. So we start with the initiation reaction, the first free radical, then it will propagate until the point that you cannot have any more hydrogens to substitute. It will terminate, and so after that, as a final product of free radical substitution, you produce an alkyl halide. Now for an alkene and also alkyne, so we have here alkene, but alkynes can be included also. We have here the presence of a pi bond, which can be a site of attack, and since these are electrons, it would attract those which like electrons, and those are electrophiles. So if you have an electrophile, it will attack this one, but the electrophile is originally coming from an electrophile bonded to a nucleophile. As a result, what would happen is that the pi bond will be broken in exchange for the bonding of the two vinylic carbons to first the electrophile, that's why it's the attacking group, right? And then the nucleophile consequently. And since we added the electrophile without removing any atom, we had an addition, and since we used an electrophile, we could say that the reaction is electrophilic addition. And we have many different electrophiles, and we have discussed them one by one in the previous videos. Now we have here an aromatic hydrocarbon, and we know that since we have an electron-rich site inside the ring, it would attract also electrophiles. And the thing here is you want to preserve again the aromaticity of this, so you do not want to break any of the pi bonds here. So what you're going to do is you're going to have the electrophile substitute one of the hydrogens, so you would be able to come up with something like, you retain these hydrogens here, and then the electrophile will be attached, and the hydrogen here will be kicked out. And so of course we know that that is substitution, and we have an electrophile attacking, so we say that this reacts by, or these aromatic compounds react by electrophilic substitution. Again, alkanes, free radical substitution. Alkenes and alkynes, electrophilic addition. And aromatic compounds, electrophilic aromatic substitution.